Auzubillahiminashaitanirrajim. Bismillahirrahmanirrahim. Assalamu alaikum dear students. My name is Danab Hamid and I am a student of B.S. Chemistry semester 6. Today I will present the topic crystal defects. There are many kinds of crystal defects. These types of the crystal defects will be discussed in this topic. First type of the crystal defect is line defects. Line defects, or you can also say line imperfections or dislocations in crystalline solids, are the defects that produce lattice distortion centered about a line. There are three basic types of dislocations. They may be edge dislocations, screw and mixed dislocations. The presence of dislocation result in lattice strain, and to strain you can also say distortion. The first type of line defect is edge dislocation. It is one of the most common crystal structure defects, and it is also called as Taylor-Orowan dislocation. Here the question arises, why it is called as Taylor-Orowan dislocation? It is named after the physicist who firstly observed the edge dislocation in a crystalline structure. This occurs when there are extra atoms inserted into the plane in the crystal lattice. As we all know, we eat corn, and in the corn structures, these corn seeds are joined in a line in a particular structures. But sometimes there is some disruptions that these structures is changed, as some of the structure is like this. The adjacent atoms are bended due to these inserted atoms, and as a result the crystalline structure is defected. The adjacent planes are not straight, as you can see there. The adjacent atoms are not straight, but instead bend around the edge of terminating planes, so that the crystal structure is perfectly ordered on either side. The second type of line defect is screw dislocation. To screw dislocation we also called it Burger's or Berger's dislocation. Berger's is a physicist whose complete name is Jan Berger's, who firstly observed the screw dislocation in the crystal structure, as the screw dislocation is also observed in the DNA structure. It is the dislocation in the lattice structure of a crystal in which the atoms are not arranged in a line, but they are in the form of a helical pattern. As I already told that the screw dislocation is like the DNA structure. As DNA structure is helical or in a spiral form, similarly screw dislocation have some helical pattern or a spiral forms. The third type of line defect is mixed dislocation. As the name indicates, mixed means that both the dislocation edge and screw dislocation components with a transition region between them. As you can see in the given figure below, that in the right side there is the edge dislocation, as the additional atoms are or extra atoms are inserted in its structure, while on the right side there is a screw dislocation which result in the formation of helical patterns. The direction of these two dislocation is combinedly given by the Berger's vector. Screw dislocation and edge dislocations are perpendicular to one another as given in the figure on the right side. And now we discuss the second type of crystal defect, which is surface imperfections or surface dislocation, and you can also say surface defects. As the name indicates, those defects that are occurred or shown at the top of the crystal, at the surface of the crystal. Surface defects are the boundaries or the planes that separate a material into regions, each having a same crystal structure but different origins. As you can see in the given figure that they have the same crystal structure but different orientations. Grain boundaries occur where the crystallographic directions of the lattice abruptly changes. This usually occurs when the two crystals begin growing separately and then meet. As in the figure, there are the planes and some kinds of the boundaries which actually separate the different oriented crystal structures. Surface defect may arise at the boundary between two grains. The row of atoms in different grains may run in slightly different directions and leading to mismatch across the boundary. Here in the figure there is a point where all the three boundaries are connected. These boundaries are known as grain boundary. Now we discuss the third type of the crystal defect, which is bulk or volume defect. In bulk or volume defect, which is three-dimensional, there are four types. They may be in the form of precipitates, dispersants, voids, and inclusions. First of all, we discuss the precipitates. Precipitates are small particles that are introduced into the matrix by solid-state reactions. While precipitates are used for several purposes, what are these purposes? The main purpose is to increase the strength of the structural alloys by acting as obstacle to the motion of dislocation. Here we discuss the first purpose of precipitates, which is to strengthen the structure of alloys by acting as obstacle to the motion of dislocation. Their efficiency in doing this depends upon their size. How much efficient the precipitates is dependent upon the size of these precipitates and also dependent upon their internal structure. However, their role in the microstructure is to modify the behavior of the matrix. Here the second role of the precipitates is discussed, that the microstructure is used to modify the behavior of the matrix rather than to act as separate phases in their own right. Now we discuss the second definition, which is dispersants. Dispersants are of large particles. As we can clearly see the difference between dispersant and precipitates. Precipitates are of small size while the dispersants are of large size. that behave as second phase as well as influencing the behavior of primary phase. Bulk or volume defects have the third basic definition, which forms the bulk or volume defect is inclusions. Inclusions are foreign particles or large particles. They are usually undesirable constituent in the microstructure. For example, we can discuss it like inclusions have deleterious effect on the useful strength of structural alloys, since they are preferential site for the failure. They are also often harmful in the microelectronic devices, such as they disrupt the geometry of the devices. Here, this is the disadvantage of the dislocation inclusion, which is due to the foreign particles, as these foreign particles enter in a microelectronic devices, they disturb or disrupt the geometry of that device, or they can alter the electrical properties of introducing undesirable properties of their own. Now the fourth one is voids. Voids are actually holes in the solids formed by the trapped gases during the solidification. When we suddenly cool a liquid or other material, which result in the interruption or trapped gases into the solid structure. These solids, trapped gases, form the holes in the crystal structures, or by the accumulation of the vacancies. They are almost always undesirable defects. Precipitates, fraction of micron in size. Dispersants may be large precipitates, grain or polygranular particles distributed through microstructure. As we know, the precipitates are the small particles, while the dispersants are the large particles, which may be polygranular or the grains in structure. Inclusion is actually the foreign particles which cause the harmful effect when they enter in a microelectronic devices. And voids are the trapped gases, decreases the mechanical strength. Importance of crystal defects. There are number of importances and properties of the crystal defects that are controlled or affected by defects. For example, the electrical and thermal conductivity in metals is affected by the point defects, while the electronic defects, electronic conductivity in semiconductor is controlled by the substitution defects. Diffusion is controlled by vacancies, while in the same way, ionic conductivity is also controlled by vacancies. Plastic deformation in crystalline structures or materials is controlled by the dislocation. Dislocation, here the dislocation of any type, of any kind, as it may be of line defect or line dislocation or mixed dislocation, screw dislocation, it is of any kind. The color of the crystal structure is affected by the defects, as some kinds of defects, as if we suppose that there is a point defect in the structure, then it affect the color of the crystal structure. Mechanical strength of the crystal structure is strongly dependent on the defects. As defects vary, the mechanical strength of the crystal structure is also varies. Now, dear students, we will discuss the effects on electrical, optical and magnetic properties. How these properties are affected by the crystal structures. The effect of the point defects on the electrical properties of semiconductors is dramatic. It is deleterious. The entire microelectronic industry critically dependent upon the successful incorporation of substitutional dopants such as phosphorus, acetine, boron, and aluminium in silicon and other semiconductors. All these semiconductors or microelectronic industry is affected by or dependent upon the crystal defects. These dopants allow us to have significant control of electrical properties of semiconductors. Devices made from silicon, gallium acetine, amorphous silicon, etc. All these are critically dependent upon the presence of the dopant atoms. As the dopant atoms changes, the amorphous silicon structure is also changes. We can also make N-type silicon and P-type silicon. How we can make N-type silicon? N-type silicon is formed by the introduction of phosphorus atoms in silicon, while the P-type silicon using the boron atoms in silicon. Similarly, a number of unsatisfied bonds in amorphous silicon are completed by incorporating hydrogen atoms. The effects of such defects such as dislocation on the properties of semiconductors is usually deleterious. Dislocation and other defects including the point defects can interfere with the motion of the charge carrier in the semiconductors. As in the semiconductors, these dislocations may act as a hindrance or resistivity in the pathway of atoms or charges. Point defect also cause increased resistivity in metals. In some cases, defects can enhance certain properties. For example, incorporation of calcium oxide in zirconium oxide causes an increase in concentration of oxygen ion vacancies that increase its conductivity and make it useful for applications such as oxygen gas sensor and solid oxide fuel cells. This is actually the importance of crystal defects, that when the calcium oxide is incorporated with the zirconium oxide, it results in the increase of the oxygen ion vacancies. That also increases the conductivity. So this is a beneficial point. Defects can convert many insulating dielectric materials into useful semiconductors for potential use in sensor applications. Like sensor applications include temperature, humidity and gas sensors. Addition of about 1% chromium oxide in alumina creates defects that make alumina ruby red. Here they are giving an example that when we add 1% of chromium oxide in alumina, it creates a defect which result in a color change, ruby red, as we already discussed. Dear students, there are many importance of crystal defects. These are as follows: as the nanocrystal of materials such as cadmium sulfide in inorganic glasses produce glasses that have a brilliant color. Different types of colors or some of the photosun glasses are also formed with the help of these nanocrystals. formed of the cadmium sulfide. Nanocrystals of silver halide and other crystal also allow formation of photochromic and photosensitive glasses. Photosensitive glasses help us to avoid the ultraviolet radiations coming from the sun, which are defective or which can affect our eyes. Many magnetic materials can be processed such that grain boundaries and other defects make it harder to reverse the magnetization in these materials. The magnetic properties of many commercial ferrites used for the loudspeaker devices. This is also the plus point of the crystal defects, that as the magnetic properties of ferrites changes, these can use for the loudspeaker devices. In wireless structures, as mentioned before, the presence of domain affect the properties of ferroelectric, ferromagnetic and also the ferrimagnetic materials. This is the end of my presentation. I hope you all get the concept. Thank you so much. Allah Hafiz.